Okay, so we are going to analyze Fourier. So we are going to study Fourier analysis. Okay, we are going to study Fourier analysis. This is for discrete time and sequence. For discrete time sequence. So you already learned this for continuous time signal. Okay. There we learn two types of Fourier analysis. One is Fourier series, other one is Fourier transform. Fourier series we use for analyze periodic signal, and Fourier transform we use to analyze non-periodic signal or aperiodic signal. Periodic signal. Okay. And in signal and system under Fourier series, you have learned complex exponential Fourier series representation and um, trigonometric, trigonometric, trigonometric Fourier series representation. These two type of Fourier series presentation we have learned. Okay, so here also we are going to learn these two. Okay, that is for discrete time Fourier discrete time signal. That is for discrete time signal. But this time we are going to evaluate discrete time signal. Discrete time signal. Discrete time signal. We are going to evaluate discrete time signal using Fourier series analysis. Okay. So, so we will first learn. We will first learn um, discrete time. Discrete time complex exponential Fourier series representation. So we have already learned, okay? For continuous time, we have already learned this concept, okay? For continuous time signal, we have already learned this, okay? So same thing is there for discrete time signal also, okay? So maybe for continuous time signal, we can remember that, okay? So a signal xt, okay? So any signal, we can say any signal, uh, the signals we are dealing in day-to-day life. Okay. Okay. So almost all the signal we are practically involving can be represented as a sum of complex exponential terms. Is a sum of complex exponential terms with the weightage. Okay. So this k can be from 0 to k can be from minus infinity plus infinity. So this is an integer. K is an integer. K is an integer. It can be minus infinity to minus 3, minus 2, minus 1, 0, 1, 2, 3, so on up to plus infinity. So this k can be 0 to minus 0 plus infinity integer value. And this omega naught we call as fundamental frequency. This is fundamental frequency. Actually, here this is angular frequency. Angular frequency. Okay, fundamental frequency. That is the angular frequency omega naught. Okay, so that is equal to Q5 T. This T naught is the fundamental period. So we can represent it like this. Okay, and also this Ck, this is a weightage, okay? This Ck is the weightage, okay? And this is referred as complex exponential Fourier series coefficient. The Ck is said to be Fourier series coefficients, okay, coefficients, okay. So there can be coefficients from C minus infinity to likewise C plus infinity. Right? And this coefficient Ck, this coefficient Ck can be evaluated with this integer. That is, this integer should be within a period, one period, one cycle. This should be in one cycle within a period. You know, so the given signal should be multiplied by j t and t. Okay. So this is the continuous time Fourier series representation. Continuous time complex exponential Fourier series representation. Okay. Like this. This is one. Okay. And this one is the so this is how we represent this. A signal as a collection of complex exponential terms. Okay. So with the weightage, this weightage is referred as complex exponential Fourier series coefficient or Fourier series coefficients. Okay. And Fourier series coefficients can be found using this integration, using this side integration. Okay. So you need to integrate it within a period. The signal is xt p minus jk on the okay. So that is that. Okay. So once we found this ck value, okay, using this using this k, okay. So we can find corresponding coefficients, that is C minus 3, C minus 2, maybe C minus 1, C0, C1, C2, C3, C4, likewise up to maybe infinite number of C values, okay? So here, infinite number of minus C value can be there. So it is corresponding with this K value, okay? So you can evaluate these coefficients, okay? So once you evaluate these coefficients, you can write the signal, complex exponential signal, sorry, the signal as a sum of this complex coefficients, okay? So if I expand this expression, so xt is k from minus infinity to plus infinity, sorry, ck e to the power of jk, okay. So using this identity, you can, using this identity, you can calculate these coefficients, okay, ck coefficients, okay. Then you can find this in the corresponding coefficients, okay, corresponding coefficients, so that you can write it as a collection of complex exponential terms. Okay? So once I expand this, I can write x is equal to, so maybe some terms may be there, okay? Some terms may be there. So if I start it from c minus 3, e to the power j, k is minus 3, omega naught t plus c minus 2, e to the power j, k is equal to minus 2, omega naught t plus c minus 1, e to the power j, minus 3 omega naught t. Okay, and also C naught e to the power j, omega is 0, sorry, k is 0, omega naught t plus C1 e to the power j1, omega naught t, so maybe up to plus infinity and maybe up to minus infinity. So if I expand this expression, I will get this kind of one. So it is as a collection of, so this is a sum notation, okay? This is the sum notation. This is sum notation. This is a sum notation. K from minus infinity to plus infinity. Okay? So I expand this expression, okay? My expression, even I expand leave. Okay, I just expand the expression, okay? So this is a sum, so all terms should be added together because this is a sum. Okay? So we will get, so if we expand this expression, okay, if we expand this expression, we will get this kind of way. Okay? So this is as a collection of complex exponential term. Okay. So this is the idea of the continuous time Fourier series representation, continuous time Fourier series representation. Actually, previous week also we have do the same thing. Okay. Uh, so in previous week, we have seen one continuous time example. Okay, maybe you can remember. Okay, so okay. So here in this book, so this is I have uploaded to the LMS. Okay, so you can refer this book if needed. Okay, so actually chapter 5 is related with the continuous time Fourier series analysis, which we have done in signal and system. Okay, and there are a lot of solved problem. You can solve this problem if you need. Okay, and the equations are there. Okay, so the Fourier series representation. Okay, so this is complex exponential Fourier series representation. Okay, so this is the equation. So this one I have written there. Okay, so this equation, then you can calculate this CK. You can calculate this CK by this identity for this integration. Okay, here 1 over T naught is there. I think I have missed it. Here, there should be 1 over T naught. Okay. There should be 1 over T naught is also 1 over T naught. And this should be within T naught. The integration limit should be within T naught. Okay. Okay. So these two identities is there. Okay. So using these two identity, we can represent any signal xt as a sum of, as a collection of complex exponential terms. Okay. So I have written this equation. Okay. And this is the trigonometric Fourier series representation. Okay. So any signal can be represented as a sum of cos and sinusoidal terms, and there is another terms that is actually the DC component. Okay, here it is the DC component. Okay, because there is no frequency, it is just a value, maybe 2 volt, 3 volt like this. So this is the DC component. This will be a DC component. And here also you can represent, you can evaluate this AK and VK using this identity. Okay. So that is that. This is the trigonometric Fourier series representation, but we are mainly focusing on this one. And we have mainly focused on this one in signal and system. Continuous time complex exponential Fourier series representation. Okay. So these two equations should be familiar to you to some level. Okay. Okay, but here in our course, you no need to evaluate this, but you need to have the idea. Okay. We are not going to do any calculation regarding the continuous time signal. Okay, we will do the calculation with respect to discrete time signal. Okay. So here we are not going to use this equation in our course, but I just uh, remind you it. Okay. And and we have done one example. Okay. Actually, it is under the solved problem. Okay. It is under solved problem. Okay. So as I can remember, we evaluate this one. Okay. So you are given XT signal. Okay. So that XT signal can be represented as a sum of complex exponential terms as according to this Fourier series representation. So CK you can evaluate using this integration. Okay. So here one period. This should be one T naught is the period. Here this is one period. Okay. This is one cycle from here to here. One cycle. So your integration should be from 0 to T naught. Or maybe minus T naught to plus T naught by 2. It is also within one cycle. No? So you can select any period. Okay. So here it select 0 to T naught, 0 to T naught. Okay. So integration should be done from 0 to T naught, 1 over T naught, xt, this signal e to the power jk omega naught t. Okay. So this signal 0 to T naught by 2 is A, and T naught 2 to T naught, that is 0. Okay. So 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 that 0 part you don't need to evaluate. So you have to evaluate up to 0 to T naught by 2 because it has a signal value A. So this A is multiplied. Okay. So once you evaluate this integration, you can calculate the CK. You will get the value for CK. Using that CK, you can calculate any value C naught, C1, C2, C3 likewise. You can calculate. Okay. Then after calculating, okay, so you can expand that xt like this. Okay. So this calculation, that value should be added here. Okay. So that is what you have to do. Okay. So we have seen that example in previous week. Okay. And uh, after that, we see that if we add these component together, what happens? Okay. So you can see that if we are adding the signal, so that shape is coming. Okay. So when we are increasing the number of terms, we can get very exact waveform like this. Okay. But it is not actually the exact waveform because there are some ripple here. Okay. To avoid this ripple, you have to add more and more complex exponential terms. More and more complex exponential terms. So we have learned. So that is the Fourier series representation. Okay. So now, actually this part we are not going to cover in our section. Okay. In our course, in DSP course, we are not going to cover that part, this part. Okay. We did it to get the idea. What is the Fourier series? To get that idea, we just use that example. Okay. Okay. Now actually we are mainly focusing on discrete time signal. We are mainly focusing on discrete time signal. So you need to know discrete time Fourier complex exponential Fourier series representation. Okay. This is what you should know. Complex exponential Fourier series representation. Okay. Okay. So here, any discrete time signal xn. Okay. So you know that now. We represent discrete time signal with respect to n. This is the sample number. This is sample number. Now you know this. Okay. This is sample number. Okay. So there is a corresponding time value actually. There is a corresponding time value. Okay. There is a corresponding time value. That time value is given using what? The corresponding time value is given as NTS. This TS is the sampling frequency, sampling time. sampling time, and sampling frequency is 1 over Ts. That is the sampling frequency. We have learned these things, okay? We have learned these things, all these things we have learned. Okay. So now any signal, any discrete time signal, in the same manner, we can represent as a sum of, as a collection of complex exponential term, okay, with the weightage, okay. So the same is there, okay. Okay, I have done a mistake when I'm writing this equation. What is that mistake? Can anyone identify what is the mistake I have done? What is the mistake I have done? Actually, this is not T, okay? That is the mistake I have. This should be what? This is a discrete time version. So this T should be what? Here it is not T, it should be what? This T should be what? And then what is this T? So this T is strong actually. If I put here T, it is not good. Instead of T, what we have to do? What we have to put instead of T? What is that? Because this is a discrete time signal. So instead of T, what we have to do? What we have to put? Instead of discrete time signal, what we have to put? What? Please message me. So if I put here T, it is not correct. Because for discrete time signal, we are not using T variable. So what is the variable we use instead of T? That is N, no? That is N, sample number. This one, N. Okay, not T. So this is the Fourier series representation for a discrete time uh, signal, for a discrete time signal. Okay. Now, now, so what is this omega naught? What is this omega naught? So this is the frequency. You know, actually this is angular frequency. This should be angular frequency. This should be angular frequency. Okay. So you know, okay. This omega naught normally referred as angular frequency. This is angular frequency. Angular frequency. Okay. So if we want to find the frequency, if naught, so what is the relationship? Omega naught is equal to 2 if naught. Okay. Okay. So you know that omega naught is equal to 2 divided by one cycle. This is a one. This is one cycle 2 This is one cycle time. Okay. So one circle duration angle is divided by one circle time. So you will get the frequency, angular frequency. Okay. So 1 over T naught is equal to F. Okay. So this and this equations are identical. Okay. This one and this one are identical. F naught is equal to 1 by T naught. Okay. This is for continuous time sequence. So this omega is angular frequency. And if you want to find the frequency, you can use this and identity. Okay. So actually, if you want to find F naught, that is equal to omega naught divided by 2 phi. this omega naught is divided by 2 5 is equal to omega naught. Okay, so cross product. I get the cross product. Okay. So F naught is equal to omega naught 2 5. This side. Okay. Okay. Now this omega naught is the angular frequency. Okay. So if you want to find the frequency, that is 5 F naught. Okay. So F naught will be omega naught divided by 2 5. Okay. So F naught is equal to omega naught divided by 2 5. If you want to find F naught, you can just divide this by 2 5. So you can find F naught. So this is angular frequency and this is frequency. This is frequency. For a discrete time signal, I told you that this is we called what? This one, no, this one we called what? Normalized frequency. This is normalized frequency. This is normalized frequency. So this may be a normalized angular frequency. This may be normalized frequency. Okay. So normally we use capital F to denote sometimes as I can remember. Okay. Okay. So that is the normalized frequency. What is normalized frequency? Normalized frequency is the signal frequency, continuous time signal frequency divided by sampling frequency. Okay. So that is the normalized frequency. Here you get that part, normalized frequency. Okay. So don't forget this. Don't forget this because sometimes we need to use this concept. Okay. Okay. Now, okay, let's assume that this k is from minus infinity to plus infinity. Let's assume, okay. So in continuous time, this k is from minus infinity to plus infinity. Okay. If it is continuous time, it is minus infinity plus infinity. So discrete time also we assume that it is minus infinity plus infinity. Okay. So k can be an integer minus infinity to plus infinity. Okay, like this. One, two, so on up to plus infinity. This two. Okay. And you can evaluate this Ck. Okay. So it is equal to, if we consider continuous time signal, 1 over T naught. This T naught is the period. Okay, 1 over T naught. So continuous time signal, you are measuring T naught in second. This is in second, fundamental period. But for discrete time signal, you are not going to measure it in T naught second. You are going to measure it as a sample number, as a number of sample in naught. Okay. So Ck is equal to 1 over T naught. Instead of T naught, we have to put the sample number of sample. Okay. And this is discrete time signal. Okay. So at the beginning, I told you that if there are if you want to evaluate the sum, continuous time signal has an infinite number of time values. Okay. So you can't just add them. You can't just add them. At the beginning, I told you this. Okay. Now you should make a තේරුම් අරගෙන තියෙනවා. Still, if you can't understand this, please come and meet me and ask. Okay. දැන් මෙතනදී කියලා දුන්නාට ඔක ආපහු කට්ටියට තේරෙන්නේ. Okay. Okay. So I told you this. Okay. So if there are infinite number of terms, we can't simply add this. Okay. We can't simply add all these things. Okay. For that one, we have to do the integration. If this is continuous time signal. But for the discrete time signal, you no need to do the integration. You no need to do the integration. Okay. So the add-in is enough. Add-in is enough. Okay. The add-in is enough. So you can directly get the summation because there are finite number of terms. So you can separately add them. Okay. But if there are infinite number of terms, you can't add them simply. You have to integrate. Okay. But here, there are finite number of terms, so you can simply add them, okay? So the given signal xn e to the power minus jk omega naught n, okay? So this is how we find ck value, okay? So this n maybe should be from in discrete time. Actually this is with the period, okay? So here also this should be with the period, okay? So that means maybe n from 0 to up to some level. Let's see that, okay? Up to some level, let's say that n naught, okay? Okay, within a period. Actually this is wrong, okay? This is wrong, but when we are going to evaluate this, I will fix these errors, okay? So just now, try to understand these two equations, okay? So this is the complex exponential Fourier series representation that is identical to this one, that is identical to this one. Only difference is instead of this t, we put n. This t, we put n for discrete time signal, and the second one is identical to this one. So here you have the integration, okay? Okay, but that is for continuous time, okay? But here you have a summation, okay, to find the CK. Okay. So these are the two equations we should use to how this Fourier series representation. Okay. So you need to familiar with these two equations. Okay. So if you need to refer more, okay, so you can refer chapter 6. Okay, you can refer chapter 6. That is Fourier analysis of discrete time sequence. Okay. So actually, now we are discussing chapter 6, okay? We are discussing chapter 6 of this book, okay? So you can read the introduction if you need, okay? Then this is the discrete time Fourier representation. So this equation is there. So you can remember, maybe I put here uh, k from minus infinity to plus infinity. I told you that is wrong. Actually, this is the correct one, okay? The evaluation should be from 0 to n naught minus 1. I show you that. Okay. Okay. And ck should be evaluated 1 over n naught. It is actually from 0 to n naught minus 1, not up to n naught. Okay. So I will explain it, why it is not like that. So uh, so xn e to the power jk omega naught. Okay. So we need to use these two equations to represent Fourier series. Okay. Okay. So we will do one example. Okay. I will select the example from this book. Okay. Then if any problem, you can refer this book. Okay. And you can ask me. Okay. So solve problem, you can use this, sorry, here, chapter 6. Okay. So at solve problem, discrete Fourier series. Okay. Okay. So we will try to do this one. Okay. Figure 6.6. Okay. So here, determine the Fourier coefficients for the periodic sequence Xn shown in figure 6.1. So I will take this, okay? I will take this. Here it asks to determine the Fourier series coefficients. Fourier coefficients. What is Fourier coefficients means? They are asking to evaluate this CK value only. Okay, CK value only. Okay. So that is Fourier coefficients. Okay. Okay. So we will take this example. We will take this example. Mm, we will take that example. Okay. This is the example we are going to do. Sample log. Okay. So I ask you to find complex exponential Fourier series representation for this signal. So still maybe you can't evaluate this, okay? Still maybe you can't evaluate this, but please just have a try, okay? Just have a try, okay? So to evaluate the complex exponential Fourier series representation, you have the identity that is x in is equal to sigma ck e to the power jk omega naught n, okay? And you can evaluate this ck 1 over n naught sigma it's n e to the power minus jk omega naught n, okay? So actually here I didn't put the limit, okay? So you can see that limit is not up to minus infinity, okay? But here you can put it as minus infinity to plus infinity, okay? But I will tell you why it is not, actually we no need to do this evaluation up to minus value, okay? So plus value is enough, okay? So here it is within the period 0 to n naught. Actually you have to evaluate it up to n naught minus 1, okay? So use this two equation and try to evaluate this xn as a complex exponential Fourier series representation. Okay, try to represent it, try to find the complex exponential Fourier series representation of this signal using these two identity. Okay, so just think how we can do it. Okay, just think, maybe you don't know how to do it. Okay, so maybe you are not familiar, you can't do this, but try to do this. Okay, take 5 minutes and try to do this. So this is very important. Okay, this is very important. So you need to do